Hi folks, welcome back to Physics with Captain Rod. This is going to be some homework help on numbers 12, 13, and 14 in Unit 5. So let's see, a laboratory electromagnet produces a magnetic field strength of 1.4 teslas. So that's the value of B in this problem, 1.4 teslas. Your value may vary. This is the one I'm reading. A proton moves through this field with a speed of 6.32 times 10 to the 6th meter per second. So let me write that down. Now 10 to the 6th meter per second sounds awfully fast, I realize. That's the speed of molasses in the world of protons and electrons. Part A, it says find the maximum magnetic force exerted in this region. So, all right, the magnetic force in general is calculated like this: QVB times sine theta. And this sine theta is what's referred to as a trigonometric function. And in this class, trigonometry is not a prerequisite for it. I usually, when I talk about magnetism in this class, I usually write QVB where the V is perpendicular to the B is good enough for our purposes. And this product represents the maximum possible magnetic force. So in this example, the maximum force is going to be the charge. Now, because this is a proton, its charge is 1.6 times 10 to the minus 19th coulombs. The V is the speed, 6.32 times 10 to the 6th meter per second. And then the magnetic field strength is given 1.4 teslas. And this is just a matter of multiplying this all out. Part B says, what's the magnitude of the acceleration? So that's a Newton's second law question. Remember, Newton's second law is net force equals mass times acceleration. If there are no other forces acting on this proton, then this is the net force. This is going to go here. You're going to go ahead and look up the mass of a proton and then find the acceleration. Do not be surprised if you get a massively huge value for that acceleration, because again, protons are extremely light. Right? When you look up that mass, you're going to see it's times something to the negative 27th power. So don't be surprised if you get a really big value for the acceleration. I think I'll just save, since C and D are kind of yes and no, are very short. I don't think I'm going to talk about those. I'll just let you work on those and talk about number 13 here. All right, let me clear my screen. All right, so number 13, it says an electron is accelerated through a 2250 volt from rest. All right, so we have an electron that starts from rest. So I'm going to put velocity is 0. And this electron is accelerated by a 2250 volts in my problem. That's a difference in potential. 2250 volts. Now, it's important to realize that potential, remember what it is, electric potential is defined as potential energy per unit charge. So the fact that a potential is even mentioned means that energy is going to be important. Potential is an energy-based concept. So what we can do here is apply the work energy theorem to this. So imagine that this electron gets accelerated, and we would show that using a motion diagram. Remember that as a particle is moving faster and faster and faster, the distance it travels is greater and greater and greater. And I'm going to write out the work energy theorem for this. PE1 plus KE1 plus work equals PE2 plus KE2. Now, if this electron is accelerating to the right in my picture, meaning the velocity is now in this direction, that means that the electric field present needs to be to the left. Remember that the electric field direction is defined as the force direction on a positively charged particle. Electrons always do the opposite. So if this thing is in fact accelerating to the right, like I have in my picture, that means that the field is pointing left. So this electron is accelerating towards higher potential. Keep that in mind. That's going to be relevant here. So now I'm just going to kind of go through and look at each term here. PE1 we can get from this. This is equal to the charge times potential 1. I'll just call that for now. And then KE1, this thing starts from rest. There are no external forces. The only force acting on this electron is presumably here this force from the electric field. PE2 is charge times potential 2. KE2 is 1/2 mv squared. If we take this term and move it to the left, this is going to read charge times potential 1 minus charge times potential 2 equals 1/2 mv squared. This charge can be factored out. Now, I know in this class we've not done a lot of examples like this. This is kind of a crash course really in physics. This final equation really kind of tells the story. This 2250 volts, this is the potential difference between these two spots. That's this number here. It's not V1 or V2, it's the difference between them. So that's what we're going to put here. But you have to know whether it's going to be 2250 or minus 2250. Well, remember that electric potential always decreases with the field. So potential 1 is smaller than potential 2. So if I take potential 1 minus potential 2, you get a negative number. So in this spot right here, we're going to put minus 2250 volts. Remember, a volt is a joule per coulomb. And in this spot, we're going to put the charge of an electron, minus 1.6 times 10 to the minus 19th coulombs. And then here you're going to put the mass of an electron, and then you're going to calculate the speed. You're going to get a pretty big number. Don't be surprised if it's like 10 to the 6th or 10 to the 7th meter per second. All right, next, it says what is the maximum magnetic force? So the idea is now this electron gets into this region over here where there's some sort of magnetic field. So I'm going to put a vector here for a magnetic field. And the magnetic force is given by QVB, where again the V has to be perpendicular to the B. So the charge is going to be the charge of an electron. That's what we used here. The V here is going to be what we get from this equation. And then the B is the magnetic field given in the problem. So that should be enough, hopefully, to get through this problem. I think I'll go ahead and talk about 14. All right, so number 14, it says, a uniform magnetic field is directed perpendicular to the plane of a rectangular loop, having dimensions 7.6 and 13. So I'm going to start by drawing a rectangular loop. In my example, this is 13 centimeters by 7.6 centimeters. It says find the magnetic flux through the loop. Oh, let me back up. A uniform magnetic field of 0.49 teslas is directed perpendicular to the plane. So in my example, perpendicular to this means that the magnetic field is either pointing into the screen or away from the screen. I'm going to go ahead and draw some magnetic field vectors pointing into the screen. And again, this is how magnetic fields are drawn. And they're not just inside here. You know, I can draw some of them out here. So again, these X's represent the magnetic field in this region. And what this means is if you take a compass and you place it anywhere here, it's going to point into the page. In a standard X, Y, Z, right, we would call that the minus Z direction. Right, so now magnetic flux, if you've watched my videos on magnetic flux, it's represented by this symbol, and it's equal to the magnetic field strength times the area. So in this example, the magnetic field is given at 0.49 teslas. Yours may be a different value in your homework, but that's the magnetic field strength. And then the area you get by this product, 0.13 times 0.076. And again, I just gave those in meters. And that's going to give you a value for the magnetic flux. So there's number 14. I think I'll just stop this video right there. I hope that this video helps get these problems done, and I'll keep making more. Have a great day.